Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We were discussing convergent nozzle flows. I just want to go to a point where we can do some analysis with it, and then we will move on to convergent. Actually, I want to go a little bit over divergent nozzles and then convergent divergent nozzles. Okay. So, moving on, we are going to go for convergent nozzle. We already know something about it from last class. We said that if I have a particular P naught here and a T naught here for a given gas, and I keep on changing my P back, the back pressure, okay, then if I keep on decreasing this below my P0 value, then there will be a flow starting, and if I keep going further and further, the velocity at this point will keep on increasing with it. And we said that at some point at a particular pressure, this particular system will get to a choking condition, that is the exit will go to a m equal to 1 condition, and we said that after that whatever we did with the back pressure, if I decrease the back pressure further, no change will be felt on the inside. Okay. What if I increase my back pressure at that point? If I increase my back pressure, that will be felt inside. Okay. So, this is where many books do not explain things very clearly in compressible flows books. Okay. They say the flow gets choked here, and that means that any change here will not be propagated upstream. That is not really true. If I increase the pressure here, immediately this will go unchoked, that will still happen. Okay. So, what is happening here? Only expansion fans do not go through and compression fans goes through? Not like that. Okay. Say I go to a point where I am at the critical pressure, okay, and at that point if I send an expansion wave, that is I am decreasing the pressure by a little amount. If I decrease the pressure by a small amount, then this outside ambient atmosphere is going to send out an expansion wave through this. When the expansion wave tries to go through this, it cannot go through this point, and so it is getting blocked, and so whatever the book says is all correct. Okay. But when I increase the pressure to slightly above the critical pressure, what will happen? It will send a compression wave. Okay. As I said before, moving compression waves typically move slightly supersonic. Okay. If it is only one very small change, it is almost isentropic compression wave, where we said we were very careful by saying compression waves are slightly more than speed of sound, expansion waves are slightly less than speed of sound. So, I will use that argument here and say that when we are at critical, if I increase pressure, that one single compression wave that is produced will go a little inside, and once it goes in, it is all subsonic. So, it just goes in and changes all the flow field. When all the flow field changes, there is no more sonic here. If I was already working at critical condition and I increase the pressure a little bit, the whole flow field will become subsonic. Nowhere will it be sonic ever or supersonic. It will never go supersonic ever anyways. Okay. It will go end up like that. So, this is just a feel for the flow you have to get. Okay. After some time we will give you more complicated nozzles, and you should be able to handle what will be the flow field inside kind of problems. Okay. But that is the simple physics for this. Okay. But whatever the books say is also correct in a way, by saying if I go Pb far less than, or Pb less than P critical, some critical pressure where it just choked, if I have such a back pressure, then it is going to go to a point where whatever expansion wave that goes, it will never cross this, because there is m equal to 1 sitting there. Okay. That is going to be the case. Even if I increase the back pressure slightly and it never crosses the P critical, that wave also will never cross and go through. Okay. There will be changes happening in here. We are not currently interested in solving the problem outside of this nozzle. Okay. Ideally, we could solve that problem also, and in fact, depending on whatever is the pressure here, there will be supersonic or subsonic flow outside of this area. We will deal with that after a few more classes, where we go and install jet flows from nozzles. Okay. This part will be a jet, and we won't worry about the jet currently. We will look at jets in 2-3 classes later. Okay. So, as of now we will just deal with this part inside the converging duct or converging nozzle if you want to call it. Okay. So, we are going to say if I keep on decreasing my back pressure from P0, keep on going down, there will be a point where my nozzle exit just gets m equal to 1 condition, that is the choking condition, that is a critical pressure, that particular back pressure will be called the critical pressure. If my pressure goes below that, back pressure goes below that value, then the flow inside will not see any change. That is the basic statement for conversion. Okay. We have this physical feel for things. Now, I just want to say calculate the velocity at this exit plane, u at exit. If I want to calculate, or p at exit, p at exit is easier, so we will do this. If it is subsonic, then we can say that every pressure wave will talk to the next wave, and we can say that the pressure at the exit will match exactly the pressure at outside, back pressure. Okay. If pressure at the exit, if my Mach number at the exit is less than sonic, then we will have Pe equal to P back always. Now, if it is choked, if I have a case Pb less than or equal to P critical, that is the point where it becomes sonic, then my P exit is equal to P star for that P naught. Okay. That is all it will be, it cannot change anymore. At the exit plane, if I measure pressure, it will be only P star corresponding to that particular P naught value, okay, which you know how to calculate, right? It is just 1 plus gamma divided by 2 to the power gamma by gamma minus 1, that is your P naught by P star. You can get that number. What is the number for gamma equal to 1.4? We did this in isentropic flows. P0 by P star will be 1.892 or 1.893, somewhere there. Okay. It is a nice number to remember, I told that time also. It will keep coming up several places in practical applications. Okay. It is a nice number to remember, at least for gamma equal to 1.4. Okay. So, if I have this condition, how will I put it in plot form? Say I am going to put P at exit plane versus P back. I am doing an opposite experiment, I am not increasing my P back, remember that. Okay. We are decreasing P back from P naught, so I will mark this as P naught value. So, when this is the case, what is my P exit? If my Pb is equal to P naught, what is my P exit? 0? No, that is wrong, 0 is a wrong answer. Same, it is same as what? Same as P back. Okay. So, Pe is same as P back. So, it is a linear relation. Okay. And so, it will be the same value here, this is the point there. If my Pb is decreased further, what will be my P back? It should be the same value. Oh wait, Pb, Pe, I have to mark a P0 here. So, this is my actual point here at that condition. Now, if I decrease my Pb further, this will also drop, it will be equal. So, I am going to draw a, ideally I should have made the scales equal, I did not in this case, ideally it should be a 45-degree line. Up to a point where my Pb is equal to my P star, which is my P critical. P star is my P critical in this case. If that happens, then this side also, this will be the P star. After that, what happens? After that, I still keep decreasing my Pb. Say my Pb is here currently, what will be my P at exit? Same, P star. So, it just goes along this line after that. Okay, it just goes along this line. So, in my experiment, the way I am going to do it, Pb is decreased keeping P naught constant. It starts from P naught, keeps decreasing up to P star, and it stays constant all the way up to Pb equal to 0 condition. Okay. Even if I evacuate the outside, there is nothing changing inside here till that point, that is what I will see. Okay. It is a simple curve for this case. Expressions are not very difficult to write, it is just this. You can write the expressions, I am not going to worry about that part. So, a more interesting case is the velocity. How will I find velocity given back pressure? Basically, I have to write u exit in terms of velocity, in terms of PB, that is my goal. So, if I think about it, I can write UE in terms of Mach number, that is easy to write. Okay. So, I will write UE as m exit times square root of gamma r T exit, where now I can rewrite this T exit in terms of T naught. I will just write equal to okay. This is same as minus 1 by 2, sorry. I have pulled out this from this T naught here. T naught by Te is equal to this, and so I will get to this particular form. Okay. I can write it like this, but still I have not solved the problem. I am having Me here, I am having Me here, but what is given is only Pb. So, I still have to solve this problem. How will I solve it? I have to write Pb in terms of P naught. Okay. P naught by Pb, actually I have to write P naught by Pb in terms of Mach number at the exit. Okay. That is the basic idea. What will be the Mach number at the exit if I am somewhere here? Pb is greater than P critical. I did not write that here. Pb greater than P critical, I am going to have this condition. When Pb is less than P critical or equal to P critical, I am going to have P is equal to P star. This is what I have. So, if I consider the case Pb greater than P critical, P critical happens to be P star, so I will just keep it as P star. Okay. What will this function be in terms of Mach number at the exit? Will be this function. This is a standard isentropic relation. Okay. I can use this because I have Pe equal to Pb. What I can tell is P naught by Pe is equal to this for sure. It so happens that Pb is equal to Pe, so I can say P naught by Pe is same as P naught by Pb. So, I can write this expression. Okay. Remember that always. Now, I want to rewrite this in such a way that I can get Me equal to something in terms of Pb by P naught. That is all. Okay. Once you do that, you will get to the answer immediately. So, which is 1 plus gamma minus 1 by 2 Me square is equal to P naught by Pe to the power gamma minus 1 by gamma. Now, I just rearrange this, so I will get Me is equal to this minus 1, it will become into 2 divided by gamma minus 1, sorry. So, it will be P naught by Pe gamma minus 1 by gamma minus 1, that whole thing multiplied by 2 by gamma minus 1 to the power half. Okay. This is what I will have. Now, all I have to do is substitute this Me in the UE expression we already had. Okay. Now, since I have this form, my UE expression also had this 1 plus gamma minus 1 by 2 Me square. I will just directly substitute it in terms of this. Okay. So, I will have UE equal to Me square root of gamma r T naught into P naught by Pe to the power gamma minus 1 by gamma to the power minus half. Okay. So, it will become 2 gamma and I will put a minus sign there, just leave it like this. Okay. This is what I am having. Now, I have Me equal to this, I will substitute this inside here. Okay. If If I do that, I will get to a final form. I will just write the final thing. You guys go figure out how you got it. 2 gamma by gamma minus 1 r T naught into 1 minus P by P naught for gamma minus 1 by gamma to the power half. Okay. Actually, I will write it as Pb here. You know that Pb and Pe were equal here. We wanted to write the exit velocity in terms of back pressure, but we know that when I use this, Pb is equal to Pe and it is going to be the same. Okay. So, we have written it like this. Now, if I have a special case where this is for Pb greater than P critical, P star. If Pb greater than or equal to less than or equal to P star, then I cannot do this, where P star I have to write it as P naught divided by 1 plus gamma by 2 to the power gamma by gamma minus 1. Right, you guys know this happens to be, this function happens to be 1.893, okay, for gamma equal to 1.4. You get to that form. Now, what will this value be? I can of course substitute this inside there and say that this is P star. If it is UE, it will just come out to be P star by P naught. I will just you can substitute this to be 1 plus 2 by 1 plus gamma. Okay, it will just come out to be 2 by 1 plus gamma. I can simplify it further and I will get a even smaller expression, okay, which I will leave it to you is equal to U star. I will write here. Okay, you can find that value. It will come out to be U star exactly. Okay, it will not be anything different. Okay, so we will leave that to you for now. The main thing is I can now tell after this point that my density does not change, my Mach number does not change, so my density does not change or temperature does not change beyond that point, and my velocity is the same. So, my mass flow rate is a constant after this point. Okay. When I say my mass flow rate is constant, if I plot my mass flow rate m dot versus Pb again, back pressure. If I do this, again remember that we are doing the opposite experiment. Pb starts with P naught value and then we are going to go decrease Pb from P naught all the way to 0. That is the experiment we are doing. Initially when I have Pb equal to P naught, mass flow rate is 0. After that the mass flow rate keeps on increasing, and when my Pb is less than P star, after that it is staying constant. So, I will draw it like this. It will look like this. Now, my experiment is going this way. Okay. I am starting with Pb and I am decreasing, and it is going to go like this. This is what I will see. This is why people say that if my flow gets choked, my mass flow rate cannot be increased anymore. Okay. This is a very standard statement in all books. Just be careful that they are having an assumption there, P naught is constant. Okay. In this whole thing we said P naught is constant. If I change my P naught, say I have a new P naught and I do the whole experiment again, say a higher P naught and do the whole experiment again, I will probably end up with this curve. Okay. This is again for another constant P naught, it will do something like this. That is what I will get. Okay. So, we need to be thinking about what is held constant. Anytime you are making a statement, you should know what are all your assumptions, and based on that you have to work. Okay. So, now if I go and do the opposite thing, if I keep my P naught increasing, keeping Pb constant, what will that look like? If I keep on increasing my P naught, keeping Pb constant, P naught increasing, I am using up arrow for increase, you just get used to it. Okay. Now of course I have to use P naught as my axis, okay. And here let us say again I am looking at m dot, mass flow rate through that particular nozzle. What will that look like? That is my basic idea. We have to think differently now. I am again starting with P naught equal to Pb and I am increasing now. If I decrease, what will happen? The flow will go reverse. We do not want that kind of problem, we will deal with that some other time. Okay. Let us say this is my Pb, we will just start with this, okay. And below that Pb we will not talk about it, I would not say it is 0, it will have a negative mass flow rate, we would not talk about it. But after that it is going to increase, mass flow rate will keep on increasing. I would not say it is going to go linear, it will go somehow, okay, some angle. I am not talking about what is happening here, it is not 0 here, it will be going down somehow, some other way, you will not worry about that problem. Negative mass flow rate means flow is going the opposite direction. Mass flow rate will keep on increasing like this till there is a point where my choking condition happens. How will I write that in terms of P naught? When the flow chokes, what will be my P naught value? I am having this particular flow, Pb is fixed, flow is choked at this point and P naught has continuously changed. When will it first choke? Yeah, if you remember, for gamma equal to 1.4, 0.528 of P naught is equal to Pb, okay. Or instead I do not want to think about that, I will just say P naught is equal to 1 plus gamma by 2 to the power gamma by gamma minus 1 times Pb. That particular value will be the value here, I will just call that my P critical here. So that is my P critical. Till that point mass flow rate is going to go something like this. After that what happens to mass flow rate? After that it is choked, till that point it is not choked, okay. After that it is choked does not mean my mass flow rate is constant, okay. It so happens that when it is choked I can write this relation, we did this some 2 classes before, okay. You can get to this particular form. So now I am going to say m dot is proportional to P naught, that is it is a linear relation now. If P naught increases, m dot increases, it is going to go like a straight line after that. So now my new experiment was my P naught is increasing continuously and it is going to go slightly non-linear initially and then it is going to go linear. This will be the curve. You can go figure out what should be the functionality in terms of P naught, I will leave it as an exercise, you can get to this plot, it is not very difficult to get there, okay. So I just want you to have a feel for these, okay. That is the main idea. Now you need to know these numbers for different gamma values. So we will just give it anyway, P naught by P star for gamma equal to 1.4, we said this is 1.893. For gamma equal to 1.3, this value is 1.832, and for gamma equal to 1.67, this value is 2.055. These are the numbers we have. Now of course you can go and figure out with compressibility what happens in here, okay. This will have the same explanation as we gave for expansion fan, the flow accelerates faster versus slower. I leave that as an exercise now, okay. You can go find out that with more compressibility you will find that it need not change P star so much, P star will be closer to P naught, that is what you will see, okay. Anyways, I will leave that as an exercise for you, you can get through that, it is not very difficult to go there. Any other questions on convergent nozzle? Shall we move on to divergent? We will go to divergent nozzle next, okay. We will not talk too much about divergent nozzle, there is nothing much to talk about here. I am having some duct and initially my flow is coming with P naught, T naught and some M1, at this location is my 1, and I am going to say this is my exit there is some back pressure. If I think about this problem, it's not very appealing problem, it's just a very boring problem if you think about it. If my incoming Mach number is subsonic and it is a diverging duct, we will go back to our table and we will say that subsonic diverging, it will decrease Mach number. We have already solved such problem 2 classes back, I think last class, right, we solved a problem like that. So you can just go and solve this problem, nothing great. In case this is supersonic, I will still go do the same thing. Supersonic flow, diverging means my Mach number will keep on increasing. If my Mach number keeps on increasing, again I will be having simple problem, no change, nothing like supersonic and subsonic mixed together. It's only supersonic, simple problem. Again similar way to solve. All I need is A by A star. I will know A by A star here, A by A star here. I can just find the Mach number and solve the problem. Very simple problem to look at. Okay. We did such problems already. I won't go and solve these problems separately. Okay. There is nothing special about a diverging duct, so we won't deal with it more. That is it. Okay. Now we will go for a more interesting case, convergent divergent nozzle. When I look at convergent divergent nozzle, I am going to think about any area variation. I am still assuming quasi one dimensional, steady flow and all those standard isentropic kind of assumptions. We will still keep those assumptions. We may find that some of them may break down, we will go to that after some time. Okay. If I think about this, we can go through the same analysis what we did some 2-3 classes before, where we introduced the term choking. We will again say it is a duct with area variation where there is a minimum area. If I keep on increasing my flow rate through this by decreasing my back pressure, again I have to call a back pressure here, and this is my exit plane, and I call this my P exit at the exit plane. Okay. If I keep on decreasing my back pressure, keeping my P naught constant, have increasing flow till a point where the minimum area gets choked. We did this already, I just do not want to do that part again. So, and after that, now my flow could choose several paths. Okay. That is where, that is the special thing about this problem. We already dealt with this a little bit. We said when m equal to 1 here, now my flow here, we said that we did this m1, m2, m3 kind of example some 2-3 classes back, where we said m3 can be subsonic or supersonic. We do not know when m equal to 1 here, m2 equal to 1. That is a special case. We are going to deal with that particular case now. Okay. We are going to say, I do not know what it was, but now we will start seeing what this really does. When I say my experiment is going to be Pb equal to P naught and then decrease, that is what I am going to do. Okay. I am going to decrease this after this. I am going to start using these arrows more often, and that is the easiest way to write increase or decrease. Okay. So, now when Pb equal to P naught, no flow, simple case, no fun, there is no flow, we are gas dynamics people, we want high speed flows anyways. Okay. So, after that we start decreasing back pressure. What will happen? The flow slowly starts happening, everything similar to whatever we did before. This will be the only point, this we will call the throat. The throat section is the point where I will have maximum velocity, and when it has the maximum velocity, that will be the one which will reach m equal to 1 first, because that is the highest. So, it will reach the sonic condition soon. Okay. Once this reaches sonic condition, the pressure at that point decides the flow inside this. Okay. It is actually a difficult thing to explain unless I go over some loops. Okay. So, I am telling you some statement, we will go and give a rationale for it, come back and visit the statement again. Okay. That is the only way to explain this problem, because the way we explain this problem is by first time observing nature, what it does, and then understanding this problem. Okay. So, now we will go through this in a simple system. I am going to say what really happens, then we will go and see if it really happens in nature. Okay. I am going to say, if I pick, we will cut off that top portion, we will just look at from here, Pb equal to P naught, no flow, okay, simple case. Now, I will introduce some special condition where I am going to say P critical 1, Pb equal to P critical 1, this occurs when m at throat equal to 1. Okay. When I do this particular experiment, I start with P naught and decrease Pb continuously. When I do that, whenever this happens, that particular condition is called P critical 1. I say 1 because there are more critical pressures possible. Okay. Now, when this happens, it so happens that the Mach number from 0 increases goes to Mach 1, and then it again decreases goes to some particular exit condition ME corresponding to A exit by A throat, subsonic solution. It goes through to subsonic solution. That is what I have. After this, if I decrease my Pb further, it cannot change pressure anywhere here because this area is increasing, subsonic solution. I am not going to have any good solution which will get to matching the pressure at the exit. Oh, by the way, I have to write here P exit is equal to Pb for all these cases. Okay. By the way, even in between these two cases, P exit equal to Pb. That is for the cases where Pb is equal to P naught or slightly lesser to Pb equal to P critical. Everywhere in between this whole range of Pb values, I am going to have Pe equal to Pb. Okay. For cases where m throat is not equal to 1, then I have to now think about what will be the exit pressure, exit Mach number, that is decided only by Pb equal to Pe, which will be same as what we did in convergent nozzle some time back. It will be the same function, same way of deriving it. I do not want to do it again. Okay. So, next interesting case, if I want to decrease pressure further, Pb, I have decreased pressure Pb, but Pe has to decrease. But we said it is isentropic flow. It cannot choose a subsonic solution anymore, because subsonic solution will give you some Mach number less than 1, because this is the highest Mach number possible in a diverging term. So, let us pick the supersonic solution. What will happen if I pick supersonic solution? If I go slightly supersonic across this somehow, because I want to reach a lower pressure, if I go slightly supersonic, then the diverging duct in an isentropic flow is going to tell me my Mach number keeps on increasing. What will that lead to? It will give me some Mach number at the exit corresponding to A exit by A throat. If that is the case, it will have one particular Mach number only, it cannot have any value. That is decided by the geometry of my nozzle. It cannot have any value, it feels like. So, we will pick that special case. Okay. Say whatever flow happens, let us say I somehow magically went to that particular back pressure such that back pressure is equal to P at exit and my flow is fully supersonic in this region. That particular condition is called PC3, critical pressure 3, okay, where I am going to say again m throat is equal to 1, I am going to say m at exit is equal to A at exit divided by A throat, supersonic solution. Supersonic solution. Okay. And I am going to have P exit equal to Pb, this special case. I have left a gap here. There is a whole range of values which we are missing. We said my experiment was Pb started with P naught and it goes all the way down to 0. That is the experiment I am doing. From P naught to till P critical 1, I know my full nozzle is going to have only subsonic solutions, and at this point my throat section chokes, which means below this always it should be choked. Once it choked and I keep on decreasing pressure, the choking condition will be choked only, it cannot increase anymore, it will be choked because I am keeping P naught constant, nothing will change. So, below this whole region my nozzle throat is choked. Now, I am going to look at, this is the next isentropic solution possible. there is nothing else in the middle. Okay. In a diverging duct, I can start with m equal to 1 and end up with a fully subsonic solution or a fully supersonic solution all the way up to here, nothing else. Okay. So, now it looks like isentropic assumption has to be removed at this point. I cannot keep using this anymore, because I want to force my nozzle to have a pressure something in between PC1 and PC3. I want to have some other value in between these two. Okay. Then suddenly my flow cannot use any isentropic path, it has to go a non-isentropic path. Okay. It so happens that the flow chooses to have a shock in the flow, it will have a shock somewhere inside in the nozzle. Okay. Now, if there is a shock in the nozzle, this is for the special case where PB is greater than PC1 and less than PC3. I have to go and refine this more to PC2. Okay. I have not given you what PC2 is, but it has to be PC2. I will tell you why. I will have m greater than 1 here, here of course m is less than 1, m equal to 1 at this point, I will just call it star condition, and across the shock of course m is less than 1. So, what my flow is doing is, if I have a pressure that is in between these two as my back pressure, the flow chooses to go on this path for some time, it goes well below the back pressure and then increases its pressure across a shock and then increases very slightly in the subsonic portion to come and match this pressure. It goes through a non-isentropic path to match the back pressure, exit pressure equal to back pressure. Okay. That will happen inside in between this region. Now, I will define what PC2 is. This is the path, this is the point where my shock sits at the exit plane. I will just put shock at exit. Okay. This particular board is having a lot of information, we will go and look at this again, okay. But we will go and look at it in a different order after some time, but anyways, this is having too much of information currently. What happens is, m at exit is going to be the same supersonic thing, AE by A throat deciding supersonic solution followed by a shock. And then P exit prime equal to P back pressure. When I put P exit prime, it is downstream of the shock. Shock is an infinitesimally thin region, we said. Okay. So, there are two pressures at the exit now. The shock sits at the exit and I have pressure before the shock and after the shock. Before the shock will be very low, the supersonic condition. After the shock, pressure has to be high, it is a compression wave. So, pressure will be high and that pressure matches with the back pressure. That is the way I am going to look at this. Okay. Now, I just gave you a long sermon in a way, right. I just told you this is what happens. Now, I want to give you a little proof that this really happens. So, we did some experiments in the lab with the convergent divergent nozzle. We will not worry about how we are seeing the waves in the flow currently, we will deal with that towards the end of the course. What we are doing currently is a Schlieren imaging. Okay. We will look at the movie soon. What we want to show is the particular movie is going to talk about only the region PB equal to P critical and above. Okay. It is in fact slightly above this, as in above in the sense it is PB is less than P critical and it is trying to go all the way up to PC2. Okay. My PB is going to be somewhere between PC1 and PC2. That is the kind of condition I am going to show you a movie of now. So, let us go to the screen. The imaging is done with a CCD camera and it is not very high resolution, you can see this edges coming up like this. We will live with that, that is okay for now. We can see the nozzle shape here, it is this curved converging portion and then it is diverging out this way, going out like this, and the same thing on the top also, it is a symmetric nozzle. And what you are seeing here are just edges of my glass window across. This is the region I can see. I cannot see outside of this using my flow visualization system. Okay. Now, this is my throat section, and we can see some wave like things going here. It so happens that in this particular flow visualization, if it is a bright region, it is expansion, and if it is a dark region, it is a shock. Okay. And that is what we are looking at here. What we are seeing here is there are very bright region here. This is my expansion region I am sitting with, okay. And then after that there is one discontinuous region out here which is very, very dark. Okay. That happens to be the shock for this particular problem. Currently we are picking a case where I have gone a little supersonic and then there is a shock sitting here. That is the condition I am living with. Now we will run this movie and we will see that when I change this Pb by P naught to much lower values, okay, if I decrease my back pressure keeping P naught constant, what happens to this problem? So it is changing and it stopped for a little while and it is again going to change further. The shock has moved from here to here. I will pause at this point to show you some more stuff. If you look here, now it is expanding further in this region, okay. And we did this shock expansion theory some time back where we said that if flow around a expanding corner will send out expansion waves, and you can see those expansion waves also in here. Whatever we drew on the board, you can see those coming. On the other side, it is an inverted problem. It is going to expand the other way. They are sending expansion waves. You can see all of them. These waves are visible primarily because there are small bumps in the machining. It is not very, very smooth machining. There is some bump and the flow picks it up. That is what this is. Okay. And if you go and look at each of those waves, you can find the local Mach cone angle and you can get the local Mach number at that location. Okay. So it gives you a rich information if you use this kind of flow visualization method. It gives you a lot of information. Okay. Now currently the shock is sitting somewhere here. Okay. Of course the imaging was not, it is just a preliminary imaging. I just picked it up because this is all I could get in this time. Okay. Now the shock is currently sitting somewhere here, exit of the nozzle is around there. Okay. We will continue with our process of decreasing my PB. Okay. Decreasing further. Now you can see that the darkest region happens to be this. Okay. The movie quality is not very good, otherwise you can see this going out here also. The lighting was not done very well in this image, but otherwise you can see that it's a shock is somewhere in this region and that is roughly the exit. After that we were not interested in the problem. We were interested in studying whether the shock interacts with the boundary layer on the nozzle. In this particular case it is not interacting so much with the boundary layer in the nozzle. Okay. So we stopped this particular nozzle experiment after that for this particular nozzle. Okay. Other things I will show you some other day when we are interacting with the boundary layer towards the end of the course. Okay. But the idea is when I keep my P naught constant and decrease my back pressure, I am having a shock forming somewhere from here and it just keeps going down, down, down till somewhere here. By the way, if I did the opposite experiment, continuously increase my back pressure, it will go the other way. Okay, the shock will go the reverse direction. Now I will tell you the truth about this video. I did not really do decrease of back pressure, but what I did was increase of P naught keeping back pressure the same. Okay. In both the cases it will do roughly the same thing, in fact exactly the same thing, as long as I think about Pb by P0 constant. What matters for this flow problem happens to be Pb back pressure divided by P0 the stagnation pressure. Only that matters for this problem. Okay. So whatever I told about this flow field all this time is all correct statement, nothing is wrong in there. Okay. But the actual experiment was done by decreasing Pb by P naught, by increasing P naught and not by decreasing Pb. That is the difference there. Okay. Now we will go back to the board. I will rewrite what we did in the previous board again. with some more proof from nature, we can now substantiate our claims that this is how the flow happens. Okay, of course, we can substantiate it more even if I give you pressure data from experiments and that are matching our theory. That is also one more way of doing the same thing, okay, which I do not have currently, so I cannot give you that, okay, but just believe me, that is correct. Now you want to go in more detail. I am going to have a pressure axis, I am going to call it PB axis, okay, and the absolute 0 is somewhere way down, we are not interested in absolute 0. This is my P naught, PB equal to P naught condition. At that particular line, no flow, I just have to write no flow and I won't worry about it. No flow. Now I will keep on decreasing it. There is a point where there is P critical 1. If that is the case, then the main change happens to be m throat equal to 1 at that line, okay. Before that, m throat less than 1, okay, that is between these two lines, somewhere there. Now I can still say in all this region P back equal to P, so I have to write it as P exit equal to P back. P exit equal to P back, okay. And one more thing I can say is M exit less than 1, I will write it before P back because I have a bracket there, M exit less than 1 between these two lines. Of course, at the top line no flow, so M exit is 0. At this point it is less than 1, but I can give you a design value for it, M exit design value, which we already looked at. It will be related to A by A star, A by A throat subsonic solution. That is what it will be. That Mach number will be the case. Now after this point, for all these cases, M throat is equal to 1. That never changes. Okay. Now after this case, now I have a P critical 2. I am trying to draw a relative scale of what these critical pressures are looking like. They are going to be far out here. That is how it will be. Okay, I will show you plots of things later, next class probably. Okay. I will draw this line. Now I will say one more thing. Shock inside divergence section. Shock inside my divergence section. That is the speciality between PC1 and PC2. And at this line, shock at exit. That is the special thing about this particular PC2 line, shock at exit. Okay. And the post shock pressure P exit prime is going to be equal to PB here, equal to PC2. Okay. And of course, Mach number at exit is going to be AE by A throat supersonic case, and after that there is a shock. Okay, ME prime will be subsonic across shock. If I go PC3, that will be somewhere here. If I look at PC3 line, fully supersonic divergence section. It so happens that this whole region is fully supersonic divergence section, just after PC2 everywhere. Divergence section is fully supersonic from this point onwards, and here from this point onwards all the way down M throat is equal to 1 from that point on all the way down. That is what we have. Okay. Now we just have to label this region and this region and we will go discuss more after some time. Okay. I am going to say P exit, this particular PC3 we already defined, it is fully isentropic supersonic solution, P exit equal to P back here, but anywhere in the middle it is not. Okay. P exit cannot change because the flow in the divergent portion is fully supersonic, nothing changes. So, it will come out to be whatever exit Mach number, the same value all the way up to here, till this region, everywhere it is exactly the same Mach number, nothing changes in this whole region. In fact, even further down, exit Mach number is all the same. Okay. Now, what happens here is shock outside, and here expansion outside, outside of my nozzle exit. That is what I have. Here I have shock outside of nozzle exit, here I have expansion outside of nozzle exit. I just have to give you separate names for these regions. Okay. This region is called under expanded, sorry, over expanded. This region is over expanded. Over expanded nozzle, this region, and this will be your under expanded. How will I label this as over or under expanded? Easy way to think about, from this point on it is fully supersonic divergence section. So, at the exit Mach number is going to be exactly that value, supersonic value decided by AE by A throat. So, if I am at this line PE equal to PB, if I am anywhere above, PE is going to be the same because ME is the same all the way here, but PB will be higher, which means I expanded too much, PE is less than PB here, okay, this region. That means the nozzle expanded too much, the flow expanded too much than what is needed. So, it is over expanded, okay. And in here PE is greater than PB, it has not yet expanded enough, so it is under expanded. So, it has to expand even outside of the nozzle, that is this case. Okay. We will go deal with the pressure values, how to calculate it, what it looks like, how to calculate the curves and stuff next class. Okay. Any questions on this? See you people next class.